എൻ്റെ സ്ക്രീൻ കാണുന്നുണ്ടല്ലോ അല്ലേ?
യെസ്, കാണുന്നുണ്ട്.
ഓക്കെ ഓക്കെ, റൈറ്റ്. ആരോ വന്നു. So during the last, okay, ഒരാൾ കൂടി വരുന്നു. So during the last class we have seen that an alpha process and a secondary process. Secondary process is having only it is a beta is equal to 1. I'll tell you once again. Class 5. Okay. Now, today we have to do the following things. I'll give you an overview. Animation. Slideshow from beginning. So after telling about this general process, we have to tell what are the steps involved in taking the data during while doing broadband dielectric spectroscopic experiment. ആ ഡോറ അടയ്ക്കൂ. വാതിൽ അടയ്ക്കാൻ എത്ര തവണ പറയുന്നു? Okay. So before doing an experiment, the following things have to be done systematically. First of all, we have to set the experimental parameters. Then data has to be procured. Following that, we have to analyze the data. Initial analysis had to be done before taking the sample from the instrument. This is because we open the sample bottle, then keep the sample inside the liquid nitrogen and nitrogen gas atmosphere so that it is inert, so that no moisture or oxygen would be in contact with the sample, and it would be intact without any contamination. So the moment you take it out, then there are chances that it can react with oxygen. Humidity can get attracted to the sample. So because of that, we should have a very good knowledge of how to take the data properly. Then after you ensure that data has been taken systematically, then the next step involved is data interpretation. You can see this diagram. Okay, you can see this diagram. We have taken a lot of data, and if you see that in between this particular each graph is each line is corresponding to one temperature. If you see that in between this particular, for example, this red line is absent, then you will see that data is not looking nice because it is not sequentially arranged in frequency. So that is the reason why we have to have a very good understanding of setting the experimental parameters, and we have to have good knowledge of how to handle the data in certain cases when you see that the sample is started crystallization. Then after taking the data, you ensure that data is systematically coming properly. If your data is not properly procured or acquired, then you will lose an opportunity to publish your results in a good journal, and your quality of data would be coming down, and you will lose a slight impact because of that. So first of all, we know that a liquid is cooled, and this along this line it is getting crystallized, and if you cool again, it is going along this line, showing as the crystal. So, but we are dealing with a supercooled liquid. So, because of that, what we are doing is we quickly cool the sample, then it will go along the supercooled liquid region. Then it will get, then again, if you are cooling, all on a sudden you will see a continuous, but a transition is getting occurred. This is thermodynamic transition, but it is a kinetic transition. How fast you are cooling, depending upon, you will get a different, slightly different transition path. But in general, in our case, we are generally cooling from 2 Kelvin to 10 Kelvin or 20 Kelvin. You don't have much difference. Even less than 1 degree difference, you will not get because of that. So we, for our experiments, we needn't have to worry about the cooling rate or how fast you are setting the cooling temperature. So during heating, now when you reach the lowest temperature, you are able to go down. So that depends upon the liquid nitrogen temperature, because liquid nitrogen is comparatively cheaper. But if you want to go down, you can use liquid helium. But unfortunately, liquid helium is much expensive, 10 times expensive than liquid nitrogen. So we don't do liquid helium experiments unless otherwise, if we have an important, very, very important phenomenology is there, then only we will go for a liquid helium. Otherwise, we will opt for liquid nitrogen. So if liquid nitrogen temperature is around minus 197 or minus 198, it is exactly 77 Kelvin. So if you use the instrument, you will get a temperature starting from 90 Kelvin or 100 Kelvin. That is the lowest temperature we are able to get it. So this region, the red mark region, is the supercooled region where you have to take data. And in the same way, this is the glassy region. Here you have to take the data here as well. So, but the dynamics here is very slow, very slow, very slow in the sense, if you take every 10-degree data, and if you want, you can go for 5-degree, but I generally take a 10-degree. So if you see that you are getting only 5 data, then 5 temperatures, then you can go for 5 degrees. Then in that case, you will get 10 temperatures in this region. Otherwise, if you are getting a 10 temperature, for example, I start from minus 150, minus 140, minus 130, minus 120, minus 100. Likewise, we take the data. You procure one temperature, then go for a 10-degree above. Then in between, you will see that here only you have 5 temperatures. Then what you will do is you will go for 5 degrees, so that your data would be, you have more number of data points in the glassy state. And in the supercooled region, but things are much different. Even you go for a 2 degrees, you will see this. You can see that with 2 degrees, you will see that the dynamics or the relaxation time has gone 1 decade sometimes. So the best strategy is, in every decade you need to have 2 data at least. So Likewise, you have to set the data. Once you go here, you can see that here there are 2 data or more. When you go here, you have 3 data. You have 3 data. So the best thing is, in that case, what we generally do is, above glass transition temperature, we take every 2 degrees. Then when you go here, you will see that things are not changing much. So you will take every 3 degrees. Then after sometimes you will go for every 4 degrees. Likewise, and around 10 raised to 6 or 10 raised to 7, you can even take every 4 degree, 5 degree. Likewise, you have to see which is the system you are dealing, which is the temperature range, etc. Depending upon that, you can see that uh, step that we will tell you how to take the data. Then you can see that here, every 10 degree, the change is not that much. Peak loss frequency is not getting much change. So that is the reason why we take every 10 degrees or every 5 degrees. That is what we have to take. Now, a dielectric experimental setup is schematic. This instrument is schematically we have represented here. And if you want, I can copy that in a bigger screen. I'll use slide. If you see the instrument, it is something like this. Schematic diagram of the Quattro cryosystem. Quattro cryosystem is the name of the cooling accessory. This is the instrument. This is the instrument. Here the liquid nitrogen is filled and sample is kept inside this DVAR. Then cryosystem. Then this instrument is controlling that. I'll copy that as well in a new slide. Control C, Control V. So this is the liquid nitrogen tank where you can fill almost 150 liters of liquid nitrogen. Then there would be a channel and it is connected to the other side of this cryo system or vacuum. It is double layered metallic cylinder, so that the outer temperature would be room temperature. Inside it can go to liquid nitrogen, some to 20 degrees above liquid nitrogen temperatures, or around liquid nitrogen temperature it can go without any difficulty. And this is the setup you are inserting is. This is the one, and this one is high frequency setup. And this is our broadband dielectric spectrometer. If you want, we have one in our laboratory, but this system is called Quattro cryo system. Instrument controlling the temperature, and you take the data through a computer and display. You can see the display, and schematically it is like this. You have a liquid nitrogen tank, and inside that a rod has been inserted to the liquid nitrogen, and there would be a heater. The role of the heater is, if you heat it, then liquid nitrogen start boiling and you will get nitrogen gas at liquid nitrogen is at 77 Kelvin. So the moment you boil it, you will get nitrogen gas at 77 Kelvin, and it is going along this path. And when it reaches here, we have a second heater. The second heater again heats the nitrogen gas, so that whatever nitrogen gas temperature you need for the sample, you will get it. And finally, the nitrogen is going outside. And in generally, if you are doing the experiment inside a laboratory, you keep one more pipe so that the nitrogen is going outside. Otherwise, if you are boiling the nitrogen inside a closed room, you will feel suffocation, because the oxygen nitrogen ratio would be oxygen gradually get reduced, and you will feel some sort of difficulty in managing the situation. So that what we do is, you connect the pipe and keep it outside the room, so that the nitrogen gas will be going outside. And second thing, if some sample inside is not a dangerous sample or carcinogenic sample or hazardous sample, so the gas would be going out. That is the reason why if you go to any laboratory, you will see that there would be something connected to outside. Now, when you keep the sample by inserting the sample, then there would be connectors connected to the broadband dielectric spectrometer, so that your data would be going to the computer. And there would be a temperature sensor just below the sample. There is a gold plated electrode would be there. Below that, beneath that, the PT100. PT100 means platinum resistance type temperature controller. PT100 is, its resistance would be 100 ohm at 0 degrees. That is why PT100, we are calling it as PT100. And these are all the technical name. This is called a sample cell. And according to Nova Control terminology, it is called BDS 100 and 1200. We have that. Then the gas heater is heating based on the temperature it is seeing. So there is a particular algorithm called what is that algorithm called PID. PID means, if you are heating it, PID is a particular algorithm. It ensures that smooth transit from the initial temperature to the final temperature. For example, if we are at room temperature, we want to go to 100 degrees. So initially, we know that 100 degrees is currently 30 degree, and 100 degrees is 70 degrees more. So initially it has to go fast. Then when it reaches 90 degree, then it should not go fast, so that it will correctly reach 100 degree. So that is controlled by a mathematical algorithm called PID algorithm. And this channel, even though this black, it is a double layer pipe. So the outer side is made vacuum, so that you can see that this part is vacuum. All this part, there is a white line, white channel. You can see that it is all vacuum, so that nitrogen, otherwise the humidity or ice formation you can see here. So since it is double layered, and this side is made vacuum using a vacuum pump, you will see that it is properly working. Inside you can have any temperature, outside it would be room temperature. So the working of the instrument is like this. If you heat it fast, then the gas pressure would be more. If you heat it slowly, gas pressure is slower. So if you heat it with a high power, then the nitrogen consumption would be higher. Now, if you want to go to any temperature between 90 Kelvin to almost 450 Kelvin, that is made by heating of the gas. But if you are going to very low temperature, you need at least a minimum pressure of let us say 60 millibar or 90 millibar. Likewise, this is how the instrument is working. So you will see in this display, it would be showing that pressure is this thing and sample temperature is this thing, gas temperature is this thing. All this would be displayed here on the Quattro cryo system. Now, depending upon, for example, if I see that a glass transition, roughly you can see that if your sample's melting temperature is 300 Kelvin, so its glass transition temperature is roughly 2/3 of the melting temperature. So in that case, if it is 300 Kelvin is the melting temperature, then glass transition temperature is 200. And what you do is above 200, you will take 30 data, for example, 200, 202, 204. 30 data you will take, 30 or 20 data you will take at every 2 degrees. So 200 to 240 you will take every 2 degrees. Then after that, every 3 degree, 3-4 reading, then every 4 degrees, likewise you will go that. Then below, so 200 degrees is our glass transition temperature. But sometimes it happens that someone has come. So 200, even if it is 200, we are not sure. Sometimes it happens that it is 200, 198 may be the glass transition temperature. So we will if it was 198, we will lose an important information at 198 Kelvin. So what we will do is, even if it is 200 Kelvin, we will take 2 data below that as well with every 2 degrees. So 198 is also we will take, 196 also we take. And if you are have a lot of nitrogen, then you can take maybe 194 also. Then below that, every 10 degrees would be good enough. And if you see that you don't have in between the lowest temperature and the glass transition, if you don't have, ഞാൻ കുറച്ച് ക്ലാസ്സിലാണ്, കുറച്ച് കഴിഞ്ഞിട്ട് വിളിക്കാം, നിന്റെ കാര്യം പറയാം കേട്ടോ. കുറച്ച് കഴിഞ്ഞിട്ട് വിളിക്കാം കേട്ടോ. Okay, so below that you ensure that some 10 temperatures are here. Then you will be in a good position to present your data to anyone. Then it happens that in the supercooled region, we know that it is thermodynamically not stable. Then all on a sudden it crystallizes, gradually it crystallizes, and you see that it is becoming crystal somewhere here. So you don't get data in between. So what we have to do is, you have to again heat the sample go to the liquid, and during cooling you can procure the data, missing data in between. Sometimes it happens that if sample, we have to make sure that cooling and heating recycles should not damage the sample, or sometimes it happens that above room temperature, above liquid temperature, the sample get degraded. So what you will do is, you happens at 240 degrees, sample starts crystallizing. Then what you do is, you melt it and come back to 240 and check whether the data is superimposable, whether the data is matching with the previous data. Then you note down that. Or what you will do is, you procure all the data, and finally you will again melt once again, and you match with one of the data you already procured before the sample starts crystallizing. That is the strategy you have to follow. Otherwise, we will be in an uncertain condition that whether sample is degraded or not. This you have to do, and otherwise we will not accept your data for publication. That is, and otherwise, or one other option is that you have to take a fresh sample and do these exercises and do a FTIR or NMR experiment, and make sure that your sample is not get degraded. But dielectric spectroscopy is a very powerful tool, so that if you go to the liquid state and come back, and if you see that within the experimental limit, if the sample data is superimposing with the previous data, and that itself is very good evidence that the sample is not contaminated. These are the things I have to tell you before taking a sample, or before procuring a data. So I hope you got a flavor of what are the things to be done. So we have to now going details about experimental parameters. So that has been done based on the sample parameters. So I'll go to that. What are the things we should make sure before taking the data. I'll go to one of my samples. So the following things you need to have a clear-cut understanding before doing the experiment. First thing, you need to give the frequency. What is the importance of frequency? Frequency, I'll tell you about that. Yeah. Control C. Control C. So the frequency means, if you take the data, data would be like this. So the advantage with the PowerPoint is that you can even take the data from the PowerPoint. Now, from the PowerPoint, you can see that you can see, instead of line, you can put apply OK. You can see that each point or each square dot is a particular frequency. You can see that it is starting from 10⁻⁻² and going up to 10⁻⁷. This you have to set in the, I'll format font. You have to set the frequencies. So how do you set the frequency? You have to give this value. There are other options like you can give that in between 10 raised to minus 10 raised to 7 to 10 raised to minus 2. You have to put a step like 52 points or 53 points. That I'll show you during the next class. So this you have to give what is the frequency range you are interested to take. That is what is here. Now after that, this is corresponding to a particular temperature. So next thing you have to set this, which are the temperatures you have to take the data. This I have already discussed with you. We have to have a very good understanding about what is happening above supercooled region, above glass transition in the supercooled liquid region, and below glass. So that for taking that, then only what you will get is you will get a smooth systematic data procurement you will be able to take. Then below glass transition also you have to take data. So that you have to, next thing you have to set is the temperature range. Now you can see that depending upon you can give the temperature. There are some more easy way. You can see that in between minus 40 to 0 degree every 2 degrees. There are some other options so that you will be able to instead of typing 21 data separately, you can give a step. So these two things you have to do initially. Then you have to set the location where you are keeping your data. So the some procedure or some standard format you have to follow. I generally follow the following format. Year must be put first, then an underscore, then month is put next, then third is the date. So the advantage with this is that by along with the data, you will be writing it in some register that my sample name would be there, date would be there. In between, you happen to miss the data somewhere or you don't know where is the location. Again, you can search with this so that you will be able to take out the data. Second thing, when you put the name of the sample, so you have to give this, instead of giving a full name, you have to give a short name. So this is benzophenol. I can easily understand what is the sample. It is benzophenol and orthoterphenyl, and orthoterphenyl is 33%. So this is, you have to follow this procedure, and you can put where your D drive and your name and the location you can give. This is the standard procedure. EPS is the software generated file. Then there would be a text file called log. Then a message would also be coming. The message would be, message would be showing that now minus 50 degrees temperature has been, data acquisition has been over. Now going to minus 40. All these messages would also be able to, you can take the data as well. Then temperature log will tell you how the temperature, where it is currently now, what is your set temperature, and how it is going. So it is going linearly or with a slope, or everything can be seen, and you can save that also, so that in case Sometimes it happens that you buy, somehow you make a mistake. Those things can be accessed by looking into temperature log message like this file. So these two things have to be done initially. Then after that, ആ വാതിൽ അടക്കാൻ എത്ര സമയമായി ഞാൻ പറയണത്? വാതിൽ അടക്ക്, അപ്പുറത്തെ വാതില്, ആ വാതിൽ അടക്ക്, ആ വാതിൽ എന്താ അടക്കാത്തത്? The next thing, now you can see that the epsilon double prime, there are certain case it would be less than 1. Some other case it would be less than 0.1. In some case it would be more than 10. So more than 10 means, more than 10 means the dipoles are very, very live. If it is more than 10, dipoles are very, very live. In that case, so we are giving the electric field. So electric field is what is the voltage and what is the thickness will define your electric field. We know that electric field is, so what is the voltage? You can make the same electric field, you can increase the electric field, or you can increase the magnitude of the electric field by shortening the thickness. So depending upon that, you have to properly have an understanding about what is the sample, what is its dielectric reason for its dielectric constant. Depending upon that, you have to set the voltage. So certain cases, if your sample is very highly dipolar, for example, if you are doing water experiment, water is highly its dipole moment is almost 50 or more. So in that case, if you take 3 volt, that will damage the sample. So certain cases I have done with a sample, I'll show you during next class. We gave 1 volt. With 1 volt water and sugar experiment, you spoil the experiment even by giving 1 volt. So in that case, even 0.5 volt is very luxurious for taking the data. So the voltage has to be set. Then I said you during the then reference measurement. So I told you during the last class, okay, 1 second. Yeah, this is what this is what I said. If the thickness is lesser, the electric field would be higher. So this is how, when you are taking 100 micron or 200 micron or 500 micron or 50 micron, you have to bother about what is the voltage you are giving, not DC AC voltage we are giving. The second thing, so what it is an impedance measurement, you will be giving a voltage and current is taking. So it does it like this. So before taking the sample, it takes a reference measurement. It takes a reference measurement. How do it takes reference measurement? This key would be, or this switch would be touching this side, so that by the same volt you are standardizing your instrument by taking a standard capacitor. So that is what I said in this slide, in this here, reference measurement, you can set it like 3 auto capacitors. 3 auto capacitors means when you go to very high frequencies, it will be measuring one other capacitor. Low frequency, it will be some other capacitor, like this. So reference measurement, it does based on this. You can set only one capacitor, you can have 3 capacitor for different ranges. So that you have to set reference measurement whether you need or not. So this makes your measurement very precise, because every time it calibrates your cell. Now I have said that in the last presentation. Now you are measuring the value from here, but there are cables connected in between the sample and the instrument. So there would be series impedance, shunt impedance. So this you have to set this value accordingly. Whether you need open calibration to be there, load short calibration would be there, and one more, low reference capacitor correction is all to be accommodated. So these things you have to tell the instrument prior to the measurement. Now then there is one more option. There are some samples like these liquid crystals. You will give a DC bias also, because that makes it is like this. I'll tell you that. Rajo, vaadil adakku. So before taking the measurement, you put a DC volt, so that that will make the sample in a particular. വാതിൽ എന്താ അടക്കാത്തത്? ആരുമില്ലെങ്കിൽ അടച്ചേക്ക്, അടുക്കളയിലെ വാതിൽ അടച്ചേക്ക്. So there are certain cases you need to give a DC voltage. So that is also to be, you can give that. Then these are the things you should have, and you have to set it. Then integration time. Integration time means, I'll tell you what is integration time. Now you can see that when you are at 10 raised to 3, 10 raised to 3 means with 1 second you are recording almost, in 1 second you are recording 1000 periods. 1000 period means, what is a period? This is 1 period, from here to up to here 1 period. So if your frequency is 10 raised to 3, with 1 second you are recording 1000 data. But here, to take 1 period, you need to take almost 100 seconds to get a single period. To get a single period. To take 1 period, here you need to, if you are here at 10 raised to minus 2, then for taking 1 measurement, 1 period, you need to spend almost 100 seconds. So that has been, you have to tell that maximum of 1 second or 1 period, and certain cases it is maximum of half second or 1 period. So if you set this, what it does is, if you are at below 1 hertz, it will take only 1 period, and if you are above 1 hertz, it will take the data for 1 second. And you can even take, and there are certain cases, like for example, I'll tell you, there are certain cases. ആ വാതിൽ അടക്കാൻ എത്ര തവണ ഞാൻ പറഞ്ഞു, പിന്നെ ആ വാതിൽ തുറന്നു വെക്കാം. ആ വാതിൽ അങ്ങോട്ട് അടച്ചേക്ക്. ഇത് 100 തവണ പറഞ്ഞാലും മനസ്സിലാവില്ല അവർക്ക്. Okay. Now there are certain cases. You see that I have observed that when your signal is very poor, and when you are taking data here, you are only taking one data, 1 period. So in that case, certain cases you need to take 2 periods so that it averages out the noise. And certain other case I have taken 3 periods. So 3 period, you have to understand that 3 period, if you are taking 3 periods here, 3 periods here, for taking one data, you need to take 300. For 1 period, it is taking 100 seconds. For 3 periods, you will take 300 seconds. Along with that, it has to take 100 seconds for the reference measurement. So in that case, it will be taking 400 seconds. Otherwise, if you are taking 1 period alone, it will take 100 seconds for the reference capacitor measurement, 100 seconds for sample measurement, 200 seconds. Even though if you tell that you need to have 3 periods plus one reference, it eventually taking only double the time. So in that case, what we generally do is, you remove these 1 or 2 points so that you will complete everything within the same time, because as you go down, time would be more and more. Here, if here it is for taking one measurement plus one reference, you need to 200 seconds. But when you are here, 20 seconds is enough. That is the beauty, that even if you remove these two, then at this you can see that the data signal strength is very small. So by doing this, you can see that one of them is jumping up slightly above. This would not have been here if you set such settings, and you are not getting any information from here. The important data is coming from here and here. So these are the things you have to consider when you are doing such measurement. This is how we take care of the experimental setting. This is how we set the experimental parameters. Now, having said that, yesterday or during the last class, any questions you can ask now? Okay, today during the last class, we have done the following. Today I'll show you the new program. During the last class, what we have done is we have two processes. We have two processes. Epsilon infinity is 3, delta epsilon is 7, O is 1 into 10 raised to 1, alpha this 0.1, beta 0.5. On seeing this, I know that this is alpha process. Nagami process because alpha is non-zero, beta is less than 1. Then in the second case, we have delta epsilon is 2, tau is 10 raised to minus 4, alpha 2 is 0.5, and here beta is 1. This is the reason why we are not putting that. But in general, we can put beta 2 also. Beta 2 is equal to 1. Then, so that it is, we have 5 parameters. So what we have to do is alpha 1, beta 1, alpha 1, beta, alpha 2, beta 2. So now I added one more thing. The only thing I have to make sure that this thing all to the power beta 2. So I make both process with the 5 parameters. Okay. Nothing I have done it. File, save, build, close workspace, yes. വാതിലടക്കാൻ പറയണം വാതിലടക്ക് രണ്ടെന്ന് build execute. Now the output has been generated. We can see in a graph desktop program text U is equal to MGH. I just plotted this is called diagram. Okay, now I am going to the program once again, Control V. I put it program 3. This is because in general our program can accommodate 3 fitting process. That is why I am showing you the third process as well. Parameter, Control C, Control V. Parameters of the third process. So delta epsilon, and this I am giving 2 or 3. This I am giving 1. 10 raised to minus 6. Alpha 2 is again 7. Beta 2 is this thing. So what I have to do is epsilon 2 in the same way I define the third process. Epsilon 3 is equal to delta epsilon 3. Well, similar to that tau 3, alpha 3, beta 3. And epsilon is equal to epsilon infinity plus delta epsilon 1, epsilon 2 plus EPS 3. Now, this, let us see what is happening if I dl is equal to, okay. Now we will see that we have to define the other one, real. So now I am defining three processes, alpha 3, beta 3, tau 3. File, close workspace is I save the program, build, rebuild all. Now I am compiling this. One error, delta epsilon 3 has not been defined. Okay. DEP, here you can see that DEPS1 I defined. DEPS3 I have not defined. I have defined it. Beta 3 but not set. Beta 3. Okay. Beta, yeah. This is because parameters of the third process, TPS3, O3, alpha 3, beta 3. This is the reason for the error. Build, rebuild all. Again, there is EPS3. EPS3 is the third process. EPS1, EPS2, EPS1, EPS2, EPS3. That is complex. Okay. Save, build, rebuild all, build, execute. Yeah. Now I defined it the same file. So I rename the file out3. Save, build, rebuild all, build, execute. Now we go to that origin. Now you can go here and download the third file, out3. Now if you go here, yeah, there is a small process here. We are not able to see that. Okay, to see that, what I can do is, that I'll show you in detail. 0, apply OK. Going to the program once again. I set the frequency in such a way that limit go to 10 raised to 10 and I start from 10 raised to minus 6. These are all 10 raised to minus 6. It is practically impossible to take, but this is a theoretical modeling. So tau1 I put tau1 is equal to 110 hertz. Set 10 raised to minus 2. Okay, now you will be.
Sir, step size മാറ്റി define ചെയ്യണ്ട.
എന്താണ്? Step size already defined ആണ്. കാരണം ഇവിടെ ഉണ്ട് 10 raised to 7. അത് ഇവിടെ ഇത് മാനേജ് ചെയ്യും. അത് വേണമെങ്കിൽ ഓക്കെ ഒരു മിനിറ്റ്. ആരാ അവിടെ ബഹളം ഉണ്ടാക്കി? ഒന്ന് മ്യൂട്ട് ചെയ്യും. Okay. DL I can put 0.1. Now you can see that it will be, this will manage. DEL is equal to 0.1, it will manage. If you have any doubt, I'll tell you that no problem. Build, rebuild, or execute. Now we go to this. Out 3 will be. Now you can see that there is one process here, second process here, third process is here. Now 0 to 5. Apply. Okay. Now it is very clear. There is one process here, another process here, and this is the third main process. You have to understand that one process is here, second process is here, third process here. Now, during the last class, for class 5. Yeah. Any doubt? Okay. Now, the same thing can be understood in a much more better way if you use some other software. Since we are studying the Mathematica in some other class, I'll tell you how that will give us another opportunity to understand the function in a better way. So we know that in Mathematica, if you want to plot sin x, it is very easy. Plot sin x, x is equal to 0 to 2 pi. It will generate like this. Now you want to see, there is another function, manipulate. The same thing, you will see that this is how the function is going down, 3.15. So this, some of us are learning this. That is why you can see that this is how it is going beautifully. This is very useful for the teaching purpose. In the same way, I have written a single process like this. Okay. Now the intermediate value is not properly set. That I have set in a different program. Now we know that here I am manipulating the tau. You can see that this is a single process. Now in this process, you can see a single process has been, here it is a linear scale, here it is logarithmic scale. That is why you can see every frequency what is happening. Now the question asked was, the same thing I plotted in this scale so that I will get a Kolkol diagram. You can see the semicircle. Now what will happen? So what you have to do is you have to set delta epsilon, the epsilon infinity. Epsilon infinity is 2.5, that you can see here, 2.5, 3, 3.54. Delta epsilon is 7.5. So it will start from 10, that is here, starting from 10. Now you can see here, it is starting from 10 and making a semicircle of the size is What is the size? 7.5. So it will be, the top would be 3.5. You can see that top is 3.75 is the midpoint. Now here same thing. Now you can see here two processes. Now two processes are here. Now can you imagine how the call would be here? Call would be like this. Uh, what is Rauf asked me the question. In some cases it is going down, and some cases it is like this. I'll show you by playing with the TO1 and TO2. TO1 is and TO2 are far away. For example, if I put TO1 is equal to 2 and TO2 is equal to -5. So you can see that, okay, TO1 is equal to -1. Okay. So you can see that two processes are far away. Two processes are far away. Are you able to see this? കാണുന്നുണ്ടോ? ഹലോ? കാണുന്നുണ്ട്. ഓക്കെ. അപ്പൊ ഇവിടെ എന്താ വെച്ചാൽ you can see that the first process, though it is starting from here, and at this point it is constant here, and the imaginary part is almost 0 here. So what you can see, the call is something like this. The reason is that it is flat here and imaginary part is almost 0 here. So that is why it is settling here for some time. Now we can plot and see that. You can see that it's starting from here and staying there for some time. Then slowly you can see that in this region it is staying there only. Then the second process is coming. So this was the, since Rauf asked this question, I wrote the Mathematica program for this. Now instead, if you put this 10 raised to minus 3, tau is 10 raised to minus 3, what will happen is, by the time it enters, the other process will start. So this is how. Now you can see that flat region you are not able to see. So due to this, the imaginary part is not going to 0. So because of this, you can see this. Before it becomes 0, it starts the second process. This can be seen from here. Now this program is very easy. Everything can be very easily visualized by this. Now you add one more process, you will understand that one primary process, second process, and third process. So this you can see here. Hope you understand this. Now only point I miss now is that ആർക്കെങ്കിലും എന്തെങ്കിലും ക്വസ്റ്റ്യൻ ഉണ്ടോ ഇവിടുത്തെ?
ഡയലക്ട്രിക്കിൽ എന്താ സംഭവിക്കുന്നത് സാർ ആ സമയത്ത്?
ഡയലക്ട്രിക്കില് എന്താണ് സംഭവിക്കുന്നതെന്ന് പറഞ്ഞാല് എന്തായിരിക്കും സംഭവിക്കുക? A sample has depending upon the sample molecular structure, it is like this. I'll tell you. Okay, for that I have to go to the first class slide. Video lectures, BDS. Yeah, it is here. Now you can see that this molecule, if I take this molecule, the entire molecule can rotate. So naturally, the entire molecule rotation, it takes more time. It takes more time means its frequency, relaxation frequency would be low frequency. But along with that, there is a dipole here also. Smaller part, it is a flexible part. It can also rotate, but this rotation is something like I can completely rotate and my hand can rotate independently. When electric field is applied across me by two plates are kept and I am inside the between the two plates. So when the electric field is applied, if my hand is a dipolar system, so this would be, first of all, this would be responding, and this would be responding very fast because it is so free that it is responding fast comparing to my entire body. My entire body would be slowly responding. So that is what is shown here. Here, if you go to low frequency, there is one process, and if you go to very high frequency, there is another process. This second process is coming because of the smaller subunit of the same molecule. And if you go to much more higher frequency, you will see that the moment you switch the plate to one charge positive and the other one negative, the electrons would be responding very fast. That is why the electronic and atomic contributions are showing here. If there is no electron and atomic contribution, then it would be one only. Nothing is there, it would be ending at one. That is the dielectric constant of the free space. Since there are molecules responding, you will get a higher value. Then electronic and atomic contribution, it is here. When you go to much higher frequency than the time required for the atoms and electrons move, then it will come down. So that is what is theoretically shown here. Now, only thing left here is, from the theoretical point of view, is this one. I hope you understood that.
Okay, sir. Okay. Understood.
Or you will understand after some time, because it is a learning process. Sometimes it will take some more time to understand what is, because we learn slowly. Even myself, when I was doing my PhD, I didn't understand these things initially. Then let me see. Okay. Now we have seen two process, two imaginary process, a real process as well. The next thing so the imaginary part alone has been shown here, and this part I have not shown. So this is the conductivity process, and the conductivity process is also to be added. Now that is the only thing left here. Then I think I'll take this during the next class and start the other aspects. So let me see what to do now. Now I can add that also. So for doing that, I'll go to the program, and the conductivity process, I can add it like So I'll send you the Mathematica program also. That will, you can play around with that. So we use different softwares like Mathematica, MATLAB. The best thing is you can do everything in Mathematica. But unfortunately, I am not an expert of Mathematica. That is why I am depending Fortran for generating data like this. Had I been very smart in Mathematica, I would have done everything with Mathematica so that all these things can be easily be mimicked with that. Now I have to add the conductivity only. Okay. That okay, I'll add a new. Okay. So 5 minutes, within 5 minutes, we will try to finish that also, so that all the data part we will be completing by then. Program 3, Control C, Control V. Control C, Control V is the copy paste. Now program 4, the final program. By that we will, that is, I have to add a small contribution. That is only in the imaginary part, because conductivity will not affect the real part. So I put cond, cond is equal to I conductivity term is this thing, minus I, that I can put like 0, 1. This is I put -1, so this is minus I into conductivity. Omega is 2 pi, 2 into pi into F. Omega is already here. Omega is already here. 2 pi F omega into epsilon 0. Epsilon 0 is 8.8 into 10 raised to, okay, I'll take it from here. Epsilon 0 is 8.8 into 10 raised to. This is a constant. So I.
Sir,
Parray.
sir,
Parray.
ഇത് minus I sigma divided by omega epsilon 0 ഇക്വേഷൻ ആഡ് ചെയ്യല്ലേ സാർ ഇപ്പോ?
അതെ അത് മാത്രം ആഡ് ചെയ്യാം.
അത് ഇൻട്രൊഡ്യൂസ് ചെയ്യല്ലേ?
അത് ഇൻട്രൊഡ്യൂസ് ചെയ്യുമ്പോൾ ഇവിടെ അത് മാത്രമേ കിട്ടുന്നുള്ളൂ. കാരണം അതിന് കണ്ടക്ടിവിറ്റി ഡസൻ ഹാവ് എനി സ്റ്റോറേജ് ടേം. ഈ പിന്നെ ഇവിടെ നോക്കിക്കഴിഞ്ഞിട്ടുണ്ടെങ്കിൽ ഇവിടെ ഈ റിയൽ പാർട്ടിന് ഒന്നും സംഭവിക്കുന്നില്ല, കണ്ടക്ടിവിറ്റി ഉണ്ട്. കാരണം പിന്നെ സ്റ്റോറേജ് ഡസൻ, imaginary part it is a loss term, so that is why we have to add that term. The conductivity term is minus I omega, പിന്നെ എന്തായിരുന്ന ടേം ഇവിടെ നോക്കിയാൽ മതി. ചിലതൊന്നും നമുക്ക് ഓർമ്മ ഉണ്ടാവില്ല എന്തൊക്കെ എങ്ങനെയാണ്. minus I sigma divided by omega epsilon
omega
0.
epsilon
Okay.
0.
Okay. 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 Conductivity ki pagaram I can put sigma divided by omega epsilon 0. So this is coming in the imaginary part. അപ്പോൾ നമുക്ക് എന്ത് ചെയ്താൽ മതി എന്ന് വെച്ചാൽ ഇതങ്ങോട്ട് ഇതിന്റെ കൂടെ അങ്ങോട്ട് ആഡ് ചെയ്താൽ മതി. Plus. So the real part will only be sigma. ഇത്രയും കൂടി ഇങ്ങോട്ട് ആഡ് ചെയ്താൽ മതി. അപ്പം നമുക്ക് എന്തൊക്കെ ഡിഫൈൻ ചെയ്യണം അത് ഡിഫൈൻ ചെയ്യണം. നമുക്ക് വേണമെങ്കിൽ റിയൽ സിഗ്മ എപ്സിലോൺ 0 EPS 0 EPS 0 EPS 0 has been here. Control C, Control V. Okay. E minus 12. Okay. File save, file close workspace ഇട്ടു കാരണം ഇതൊന്നും കൂടി. Now going to that program. Okay.
Sir, occasionally E0 അല്ലേ കൊടുത്തേ?
E0.
EPS0.
Okay, ഞാൻ നോക്കട്ടെ. പ്രോഗ്രാം ഓക്കെ 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 നോക്കാം. ശരിയാണത്. ഇവിടെ EPS 0 എന്നാണ്, അവിടെ ഇവിടെ തെറ്റിയിട്ടുണ്ട് അല്ലേ. സിഗ്മ E0 ഓക്കെ. EPS 0 നമ്മൾ വേറെ ഒന്നും ഡിഫൈൻ ചെയ്തില്ല എന്ന് തോന്നുന്നുണ്ട്. EPS 0 ഓക്കെ. ഇപ്പം ശരിയായല്ലോ അല്ലേ. ബിൽഡ് റീബിൽഡ് ഓൾ. യെസ്. എന്തെങ്കിലും തെറ്റുണ്ടെങ്കിൽ ഒരു സിഗ്മ സിഗ്മ നമ്മൾ ഡിഫൈൻ ചെയ്തില്ല. അപ്പം നമുക്ക് വേണമെങ്കിൽ സിഗ്മനെ ഡിഫൈൻ ചെയ്യാം. ഇവിടെ എവിടെ സിഗ്മ ഈസ് ഈക്വൽ ടു 1 e to the power minus 18 എന്നൊക്കെ കൊടുക്കാം. അപ്പം നമുക്ക് എന്ത് ചെയ്യാന്ന് വെച്ചാൽ 2 പ്രോസസ്സ് മതി എന്ന് വെക്കണമെങ്കിൽ അങ്ങനെയും വെക്കാം. ഇനി നമ്മൾ സേവ് ബിൽഡ് റീബിൽഡ് ഓൾ ബിൽഡ് എക്സിക്യൂട്ട്. ഓക്കെ. അപ്പം നമ്മൾ ആദ്യം കോളിലൊന്ന് വരച്ച് നോക്കാം. എന്നിട്ട് റിയൽ പാർട്ട് ഇമാജിനറി പാർട്ടൊക്കെ നമുക്ക് വേറെ ഒന്നും കൂടി ചെയ്യാം. ഔട്ട് 3 തന്നെ ഇവിടെ ഇങ്ങോട്ട് പൊന്തിയില്ലേ. ഓക്കെ ഓക്കെ ഓക്കെ. അത് ആദ്യം വെച്ചാൽ മതിയാണ്. അപ്പോൾ ഞാൻ ഒന്നും കൂടി കാണിച്ചു തരാം. പിന്നെ നമുക്ക് നിങ്ങൾ ചെയ്ത് നോക്കിയാലേ പിന്നെ ഇത് മനസ്സിലാവുള്ളൂ കേട്ടോ. അതുകൊണ്ടാണ് ഇപ്പൊ ഞാൻ ഔട്ട് 3 എന്ന് കൊടുത്തിട്ട് കാണിച്ചു തരാം. ബിൽഡ് റീബിൽഡ് ഓൾ ബിൽഡ് എക്സിക്യൂട്ട്. ഇപ്പം സിഗ്മാന്റെ കോൺട്രിബ്യൂഷൻ എടുക്കുന്നില്ല, അതുകൊണ്ട് കോൾ ഡയഗ്രാം എങ്ങനെ ഉണ്ടാവും നോക്കാം. മിണ്ടല്ലോ ഇങ്ങനെ ഉണ്ടാവും കോള്. ഇനി ഞാൻ എൻ്റെ സിഗ്മ കോൺട്രിബ്യൂഷൻ അങ്ങോട്ട് ആഡ് ചെയ്യാണ്. സിഗ്മ കോൺട്രിബ്യൂഷൻ 10⁻⁻14 കൊടുക്കണുള്ളൂ. കുറച്ചേ കൊടുക്കണുള്ളൂ. അധികമായി കഴിഞ്ഞാൽ ബിൽഡ്. ഇനി ഞാൻ ഔട്ട്പുട്ട് ഫയൽ 4 എന്നും കൊടുത്തു. സേവ് ബിൽഡ് റീബിൽഡ് ഓൾ ബിൽഡ് എക്സിക്യൂട്ട് ചെയ്തു. ഇനി ഔട്ട് 4 കൂടി നമുക്ക് അതിലേക്ക് ആഡ് ചെയ്യാം ഒറിജിനിലേക്ക്. ഇനി ഇവിടെ കണ്ടക്ടിവിറ്റി വരുമ്പോൾ എന്ത് സംഭവിക്കും എന്നുള്ളതാണ് ഇനി നമ്മൾ കാണിക്കുന്നത്. റീസ്കെയിൽ ഒന്നും ചെയ്യുന്നില്ല. കണ്ടോ, ഇതാണ് കണ്ടക്ടിവിറ്റിയുടെ ഇഫക്റ്റ്. അപ്പൊ ഇവിടെ ഉള്ള ഒരു ചെറിയൊരു പ്രോബ്ലം എന്താന്ന് വെച്ചാൽ കണ്ടക്ടിവിറ്റി വന്നു കഴിഞ്ഞാൽ നമുക്ക് യഥാർത്ഥത്തിൽ വി ഷുഡ് ഹാവ് എൻ ഐഡിയ വാട്ട് ഈസ് ഹാപ്പനിങ് ഹിയർ. I can have a good idea on the first process, second process. But the third process, I'm not able to understand what is happening because of the conductivity. So first of all, I have to detect the conductivity. അപ്പം അതാണ് ഇവിടെ സംഭവിക്കുന്നത്. കണ്ടക്ടിവിറ്റി വരുമ്പോൾ ഇങ്ങനെ വരും. ഇനി നമുക്ക് അതിന്റെ റിയൽ പാർട്ട് എന്ത് പറ്റും, ഇമാജിനറി പാർട്ട് എന്ത് പറ്റുന്നു. ലെറ്റ് us see what is happening there. With another 5 minutes, I'll finish it off. Okay, file, close workspace, yes. അപ്പം ഞാൻ ഇനി റിയൽ ഇമാജിനറിന്നും കൂടി പറഞ്ഞിട്ട് അങ്ങോട്ട് കൊടുക്കാം. പ്രോഗ്രാം ഫോർ Ctrl+C, Ctrl+V. Program for real. Now I am looking into what is happening to the real part. So conductivity is there. What I am trying to plot is a real frequency. What is frequency? FREQ. Real EPS. Now I put the name of the file, R file, build, rebuild all, yes, build, execute. So real part I am trying to generate origin. റിയൽ പാർട്ടിൽ എന്താണ് സംഭവിക്കുന്നത് എന്നുള്ളതാണ് നോക്കുന്നത്. സോ ഐ എം ട്രൈങ് ടു ഗോ ടു ദി ഡെസ്ക്ടോപ്പ്, പ്രോഗ്രാം, ടെക്സ്റ്റ്, പ്ലോട്ട്, ലൈൻ, linear, log 10, apply, okay. Scientific, apply, okay. 1, 2 or 3 is okay. So the real part, this is the first process, second process and third process. So real part, ഇനി ഞാൻ എന്ത് ചെയ്യുന്നു വെച്ചാൽ I am removing the conductivity so that you will get an idea. Even the conductivity is not there, what will happen? Build. അപ്പൊ ഞാൻ 0 എന്ന് കൊടുത്തു. സിഗ്മ 0 ആണെന്ന് മനസ്സിലാക്കാൻ വേണ്ടി. ബിൽഡ്, റീബിൽഡ് ഓൾ, ബിൽഡ്, എക്സിക്യൂട്ട്. ഇനി ഞാൻ ഇതേ ഗ്രാഫിലേക്ക് തന്നെ ഇവിടെ നോക്കിക്കഴിഞ്ഞാൽ 0 കൂടിയുണ്ട്. ഈ ഒറിജിനിൽ പോയിട്ട് റിയൽ പാർട്ടിലേക്ക് അതും കൂടി ഇങ്ങോട്ട് കൊണ്ടുവന്ന് നോക്കാണ്. 0. ഇനി 0 എടുത്തു കഴിഞ്ഞപ്പം ഇവിടെ 2 ഗ്രാഫ് ഉണ്ട്. ഇത് രണ്ടാമത്തെ ഗ്രാഫ് റെഡ് വിത്ത് ലൈൻ സ്കാറ്റർ ഇങ്ങനെ കൊടുക്കുന്നുണ്ട് കേട്ടോ. അതിന്റെ മേലെ കൂടെ തന്നെ പോകുന്നത്. അപ്പൊ റിയൽ പാർട്ടിൽ കാര്യമായ ഒരു മാറ്റവും സംഭവിക്കുന്നില്ല. Now let us see. I'll save project as desktop. Okay. Program real part. ഇനി നമുക്ക് ഇമാജിനറി പാർട്ടിൽ എന്താ സംഭവിക്കാൻ നോക്കാം. അപ്പൊ ഞാൻ എന്ത് ചെയ്തു വെച്ചാൽ ഫയൽ, സേവ്, ഫയൽ, ക്ലോസ് വർക്ക്സ്പേസ്, യെസ്. ഇനി നമ്മള് 4A എന്നുള്ള മാതിരി 4I എന്ന് കൊടുക്കാം. ഇമാജിനറി പാർട്ട്. Ctrl+C, Ctrl+V. ആ വാതിലടക്ക് സംസാരിക്കല്. 4I. So by this we will file, build, rebuild all. Yes, this is the imaginary part without sigma. build, rebuild all. Now what I am doing is if you want, what you can do is you can remove these parameters so that the process would be more, third process you can make it to 0. You can make it to 0 by making delta epsilon to be 0, so that will not be coming at all. Build, rebuild all. Okay. Build, exit. Okay, I have to name the file as, instead of R, I put I, imaginary part with the sigma 0. Build, rebuild all. Build, execute. അവരൊരു മിണ്ടായിരിക്കാൻ പറയും. I 0. Imaginary is 0 now. Now the real part I removed it. Okay. Okay. Okay, 1 second. We have to see. Yeah, I made a mistake. I didn't define what has to be written. It has to be imaginary minus imag, imaginary part of build, rebuild all, build, execute. Okay, executed it. Now I have to go to the origin. Here I downloaded the imaginary part. You can see that. So you can see that this here it is more first process, second process, a very weak third process is also the. Now you can start from 0, apply. Okay, starting from 0. Now if you give the conductivity, now the conductivity, if you are giving the conductivity non-zero conductivity, so I0, I put I, save, build, rebuild all, build, execute. Yeah. Now executed it. Now go to this program. Now you for I. Now you can see that for I also putting with the line, apply. Okay. Now this is the effect of conductivity. Conductivity is because there is a 1 by there is a term called conductivity has a contribution 1 by frequency. 1 by frequency is as frequency increases, omega is 2 pi f. As frequency increases, its effect would not be seen. ഇവിടെ നോക്കിക്കഴിഞ്ഞാൽ you can't see any effect. But as you go to lower frequencies, its effect is coming up. Now, what I am doing is I am putting the y-axis also in the logarithmic scale. Linear log 10, apply. Okay. Now you can see that in logarithmic scale, this is the effect. So to make more understanding on that, you put major grid. In major grid, if you put, okay, I'll put it, we are only 10 raised to minus, okay. We need to 10 raised to 4, up to 10 raised to 4 I am plotting. Now you can see that this is -1 because you go to 1 decade right, your y is coming down. Now the same slope. Now I put it with a different color, blue with 3. Slope is, you can see that this was the question I asked. What is the, how do you identify a process, whether it is a process or a conductivity? Conductivity would be having a slope of -1. A dielectric process, generally, it is not always, generally it will be having a slope -12. Red 2. You can see more or less it is less than that. Okay. All that depends upon your beta value. Generally, it is 0.5 in many samples. But conductivity, if it is conductivity, it is -1. With this, I stop today's class, and any doubt we can spend 5 minutes and stop the recording right now. I'm stopping the recording. If you have any doubt, I stopped recording. Stopped. Any question? 5 minutes we can spend for questions. Then anyway, I will be sending you the video as well as the Mathematica program and all the other details. So, Rauf, did you understand what is happening? The question you asked in Mathematica?
മനസ്സിലായി സർ.
ഇത് ആഴ്ചയിൽ ഒരു ക്ലാസ് ഉള്ളെങ്കിലും കാര്യമായിട്ട് ഞാൻ പഠിപ്പിക്കുന്നുണ്ട്. അതിനെക്കൊണ്ട് അത് നിങ്ങൾ ചെയ്താലേ നിങ്ങൾക്ക് മനസ്സിലാവുള്ളൂ. ഇത് ചെയ്യാത്തവർക്കൊന്നും ഇത് മനസ്സിലാവില്ല. അരുണിമ ഓണാണോ? ഓക്കെ, മനസ്സിലാവുന്നുണ്ടോ?
കുഴപ്പമില്ല, ഞാൻ നോക്കാം ഒന്നും കൂടി.
ഇനി എന്തേ ക്വസ്റ്റ്യൻ ഉണ്ടോ?
സാർ ഇത് ചെയ്തു നോക്ക. ഫയല് സാറ് സെൻഡ് ചെയ്തിട്ടെ.
ഞാനിതെല്ലാം സെൻഡ് ചെയ്യാം. നിങ്ങള്
ചെയ്തു മാത്തമാറ്റിക്സ് ഭയങ്കര ഇൻട്രസ്റ്റിംഗ് ആയിട്ടുണ്ട്. മറ്റേ അതിങ്ങനെ വേരിയബിള്
മാറ്റുന്നില്ല. ഞാനത് വളരെ ഷോർട്ടായിട്ടേ പറഞ്ഞിട്ടുള്ളൂ. പക്ഷേ പിന്നെ മാത്തമാറ്റിക്ക വളരെ എളുപ്പമാണ് ഇത് ചെയ്യുന്നത്. മറ്റേ ഇതെല്ലാം ഈവൻ സൈനക്സ് തൊട്ടിട്ട് ഇതൊക്കെ മാനിപ്പുലേറ്റ് എന്നുള്ളത് നമുക്ക് ഗോവിന്ദരാജ് സാറ് പറഞ്ഞു തന്നേന്ന് ഞാൻ ചെയ്തതാണ്. അത് ഞങ്ങളൊരു മാത്തമാറ്റിക്കൽ
പ്രോഗ്രാം ഡാറ്റ ജനറേറ്റ് ചെയ്ത് ആ ഡാറ്റ ഒറിജിനൽ വരച്ച് നോക്കുമ്പോൾ
ഇവിടെ ആകുമ്പോ തന്നാല് എനിക്ക് പിന്നെ റൌഫ് ക്വസ്റ്റ്യൻ ചോദിച്ചപ്പോൾ ഞാനത് PhD-യുടെ സമയത്ത് ചെയ്തിട്ടുണ്ടെങ്കിലും ഈ പ്രോഗ്രാം ഇത് ഇങ്ങനെ ചെയ്യാൻ പറ്റിയപ്പോ എനിക്ക് തന്നെ ഭയങ്കര ഇൻട്രസ്റ്റിംഗ് ആയിപ്പോയി.
നമുക്ക് ആ സ്പോട്ടിൽ തന്നെ കാണാൻ പറ്റില്ല വേരിയബിൾ എന്താ കണ്ടക്ടിവിറ്റി ആണ്.
ഇതിൽ തന്നെ നമുക്ക് 2 പ്രോസസ്സ് ഇൻഡിപെൻഡന്റ് ആയിട്ടും വരയ്ക്കാൻ പറ്റും. ഞാൻ പിന്നെ ഇതെല്ലാം കൂടി ആകുമ്പോ നിങ്ങൾക്ക് അത് കൺഫ്യൂഷൻ ആവണ്ട.
കുറച്ച് വെച്ചിട്ട് മതി, എന്നാലേ ഒരു പെട്ടെന്ന് മനസ്സിലാവുമല്ലോ, ഉൾക്കൊള്ളാൻ കുറെ.
അതെ. ഈവൻ നമ്മുടെ GG സാറ് വായിക്കുമ്പോ ഇതിന്റെ ഇടയിൽ ഈ വേറെ ഒരുപാട് കമന്റ് ഉള്ളതുകൊണ്ട്
ഞാൻ വിചാരിച്ചു സാറ് കണ്ടക്ടിവിറ്റി വേറൊരു ക്ലാസ്സിൽ മാത്രമാക്കി ആയിരിക്കും പറയാന്ന്.
ഇത് പിന്നെ കണ്ടക്ടിവിറ്റി ഒരൊറ്റ ടേം ആഡ് ചെയ്യാനുള്ളതുകൊണ്ട് അതോടെ ഇത് തീർന്നോട്ടെ വിചാരിച്ചിട്ട്.
ഓക്കെ.
അപ്പോ എന്നാ ഞാൻ നിർത്തട്ടെ എന്നാല്. ഓക്കെ
ഓക്കെ എന്നാൽ
ഗുഡ്
ശരി.
നൈറ്റ്
ഓക്കെ
ടു
ഗുഡ്
യു
നൈറ്റ്.
ഓൾ.
Okay, good night. Thank you.